Today, I'm going to explain Thevenin's theorem and the interaction between output impedance and input impedance. As I often do, I'm going to express Thevenin's theorem a little differently from what you might see in textbooks, and that is, Thevenin's theorem states that any circuit that produces an output will act exactly like a circuit that has a single voltage source with some impedance in series with that voltage source. Since we're talking about DC circuits, we're going to reduce that voltage source to just a battery with a resistor in series with it. So Thevenin's theorem says that any circuit, no matter how complex, that produces an output will act like a battery with a resistor in series with it. And so how do we determine what those are? Well, let's take a look at how we can do that. First, we start by putting a voltmeter across the output. This will give us what's called the open circuit voltage. Remember that the voltmeter has a very high impedance, so for all intents and purposes, it has no current flowing through it. So we have an open circuit here. So we're going to measure a voltage. Let's say we measure 5 volts. So what does that tell us? Well, we know there's no current flowing through this resistor because it's an open circuit. And to get a voltage differential across that resistor, we must have resistance and current. There's no current, so there's no difference in the voltage from here to here. So whatever voltage we have here is the same voltage we have over here. So by measuring the open circuit voltage, we've just determined that this is a 5-volt battery. Now how do we figure out what the resistance is? Well, now we replace this voltmeter with a current meter and measure the current. So let's say I measure that and I have 100 milliamps. So what does that tell us? Well, we use Ohm's law, divide the 100 milliamps into the 5 volts, and that gives us 50 ohms for the resistor. So that's the basic way we find out what the Thevenin equivalent circuit is. Now this is a circuit, let's say it's in a black box or something, we don't really know what is there, but it acts like a battery with a single resistor in series with it. Let's take a circuit and see how this works. I'm going to make a fairly simple circuit up here. I'm going to write it up here so I have room to do the Thevenin equivalent below. So here's our battery. Make it a simple circuit so we don't have to get to thinking too hard about it. Let's make this a 20-volt battery. Make this a 1K resistor and another 1K resistor. And we'll put a couple of terminals here which will constitute the output of that circuit. So what we're going to do now is measure the open circuit voltage by putting a voltmeter here. Now that's the open circuit voltage. This is a closed circuit here, but over here we have an open circuit, so there's no current flowing through the voltmeter. Let's draw the Thevenin equivalent circuit here and find out what we find out by doing this. So we measure that voltage. What do we get? Well, we have 20 volts here and we have 2 equal resistors. So we know the voltage across these resistors will be equal and they must add up, because it's a series circuit here, they must add up to this 20 volts. So that's going to be 10 volts across this resistor and 10 volts across that resistor. So we measure 10 volts. So our voltmeter measured 10 volts, and as we explained before, that must be the battery voltage. That's a 10-volt battery. How's that work? Well, stay with me. We'll see that it does act like this. How do we find out what that resistor is? Well, now we take the current. So we remove the voltmeter, replace it with a current meter, and measure how much current we have. How much is that going to be? Well, the current meter is essentially a short circuit, so basically it eliminates that resistor because we have a 1K resistor in parallel with a 0 ohm resistor, and we know that when we have 2 resistors in parallel, or any number of resistors in parallel, the total resistance will be lower than the lowest resistor. Well, the lowest resistor is 0 ohms, and we can't get any lower than that, so together they are a total of 0 ohms. So basically that's no longer part of the circuit. So now we measure our current, and we find that with 20 volts and 1K, we're going to get a current of 20 milliamps. So now our current meter, 20 milliamps. So what does that tell us? Well, we have a simple series circuit, 10 volts, 20 milliamps, and some resistance. To find that resistance, we divide our current into our voltage. If you know your voltage, you divide into it. So 20 milliamps goes into 10 volts. That gives us a resistance of 500 ohms. So the Thevenin equivalent circuit of this circuit equals that circuit. So this circuit, looking at the output here, will act exactly like that circuit. Well, if that's true, then if we put some kind of a load out here, we should get the same results here as we do here. So let's try that. Let's put a 1K resistor out here as a load and find out what we get. So we'll do the same thing here. And if this circuit acts like that circuit, we should get the same voltage and current, of course, through the load here, because that's another 1K resistor. Let me pull out my calculator because I certainly won't be able to do these calculations in my head. So let's find out what we have here. Okay, so let's find out what the voltage across here is. That's going to be, we have two 1K resistors. Together they are how much resistance? Equal resistors in parallel will give you half the resistance. So the total resistance of two 1K resistors in parallel will be half of either one or 500 ohms. We put that in series with this, so we have 1K plus 500 ohms. That gives us 1500 ohms of resistance total. So that's going to be divided into the 20 volts. 20 divided by 1500 gives us a total of 13.3 milliamps through that 1K resistor. So how much voltage are we losing there? So that's going to be 13.3 milliamps times 1,000. And that gives us 13.3 volts across here. Leaving us, take 20 volts and subtract 13.3 volts, and we're going to get left over here 6.66 volts. And of course 6.66 volts with 1K is going to give us a current, let's try that again, 6.66 volts divided by 1,000 equals going to give us 6.66 milliamps. Okay, so we put this load out here. Let's break this right here. Just to remind us, this is the load we're putting on the circuit. So we put a 1K load across that circuit. We got 6.66 volts across it with 6.66 milliamps. Okay, now if this circuit really does act exactly like that circuit, we should also get 6.66 volts across this resistor. By the way, I did this by Ohm's law, but we could have also done it as a voltage divider. Here we have 500 ohms and 1,000 ohms, so we have 2 times the resistance we have here. So 2/3 of our voltage would be here and 1/3 of our voltage could be there. We could just take our 20 volts and divide it by 3, and that gives us 6.66 volts, and we do that division, and that gives us the voltage across the lower resistance. This is 500 ohms. We'd have 6.66 volts. So I did that by Ohm's law, but don't forget these things can be a lot easier than they look. Once again, 500 ohms, 1,000 ohms. Twice the resistance as here, so twice the voltage. So 20 volts, divide that by 3. 1/3 goes here, 2/3 goes there. And could have figured that out a little easier, but I did the Ohm's law just because I could. Now we're going to do the Ohm's law and find out if this circuit gives us the same voltage here as that circuit. Well, what do we have? We have 10 volts, and we have, what, 1,500 ohms? Divide that by, and we get, lo and behold, 6.66 volts. So indeed, this circuit acted exactly like that circuit. If we look at it as, there's that circuit, and there's that circuit. So we took this complex circuit, slightly more complex, and reduced it down to this Thevenin equivalent circuit. And no matter how complex this is, it would have worked. I could have used a more complex circuit, but that may have caused us to lose focus on what we were doing. So we did see that this circuit did act like that circuit. So we have a 20-volt battery, two 1K resistors. Taking the output across the second 1K resistor acts exactly like a circuit that has a 10-volt battery and a 500 ohm resistor in series. So what does that do for us? Well, understanding Thevenin's theorem is a big step to understanding what output impedance is, because the Thevenin equivalent resistance, or in the case of an AC circuit, the Thevenin equivalent impedance, is the output impedance of that circuit. So let's erase this. And draw a circuit. We know that any circuit, well, let's do this with an AC circuit just because we can. So there's an AC voltage source and some kind of impedance. So some AC circuit that produces an output will act exactly like a circuit that has a single AC voltage source and a single impedance in series with it. And this Thevenin equivalent impedance is the output impedance. So something you'll hear a lot about is output and input impedance. We're going to talk about that in just a moment, but that's what your output impedance is your Thevenin equivalent impedance. We're going to go back to working with a battery and resistor because we're doing DC and we don't want to get into AC for quite a while. So let's take a look at a typical circuit reduced to its Thevenin equivalent. So we have a battery and a resistor. Now this is going to be connecting to some other circuit, even if it's connecting to some kind of device that's not a circuit. For example, if this is a radio transmitter, it's going to attach to an antenna. Well, that's another circuit. So we always have one circuit going to another. Does the antenna go to another circuit? Yes, it couples to the luminiferous ether to create radio waves. So everything is coupling to somebody else. And so that other circuit does not produce an output, it's an input, so it's passive and it takes the energy from the previous circuit. And when we do that, we have that represented by a single resistor. So here's our output impedance, just a resistor here, not the complex impedance we have in AC circuits. And over here we have the input impedance. So every circuit will act like that. So we have a circuit, and then the input impedance, of course, is the load that we put across there. So how do these interact with each other? Let's get the clutter away here for just a minute so I can write on the board. And a couple of things to remember, a little mantra, if you will, is that a high impedance, like a high resistance, is associated with a low current. And a low impedance, I'm using the Z for impedance. Since this is a DC circuit, we could use ohms. Z represents a complex impedance you have in AC circuits, but this could be ohms. I'm just using Z because we're talking about impedance. I'm going to use the symbol for impedance, but that could be an omega if we were talking about DC circuits and simple resistors. So high impedance is associated with low current. Low impedance is associated with what? Guess what? High current. So basically, if you have a high resistance, you're going to have a low current. If you have a low resistance, you're going to have a high current. So low impedance, high current, high impedance, low current. Now let's see how that works when they interact with each other. I'm going to leave that up there for now. So let's say we have two circuits coming together. Let's just show a little connection here. Here's our output impedance, and here's our input impedance. And let's say we have a low output impedance and a low input impedance. So let's draw that this way. Low impedance, low impedance. What's that saying? The load is saying, or the input impedance is saying, I'm a low impedance, I need a lot of current. Low impedance, high current. This is saying I'm a low impedance too. I can give you a lot of current. So they work well together. Now let's see what happens if we have a high impedance. This high impedance says, I cannot give you much current. I'm a high impedance. I can only give a small amount of current. This is a high impedance. It says, I'm a high impedance too. I don't need much current. I can't give much current. I don't need much current. They work together. Now let's see what happens if we have a low impedance here and a high impedance here. Now we have a mismatch. Let's see if that's a problem. This says, I'm a high impedance. I don't need much current. This says, I'm a low impedance. I can give you all the current you want and more. No problem. So a low impedance going to a high impedance is usually no problem. Now it can be sometimes. Well, what happens is when we have a low impedance going to a high impedance, we pretty much maintain the voltage because since we have a low resistance here, or low impedance, we don't have much of a voltage drop. So the voltage here is pretty close to the voltage over here. So we maintain that voltage. So if we want the output voltage to remain high, well, we have a high impedance input to go to, and if we have a low impedance output, that just helps that voltage be maintained. The only problem is sometimes you might want that voltage to be lower. One particular case is with audio systems where you have microphones, and if you have a low impedance microphone going into a high impedance input, you're going to develop too much voltage there, and that causes distortion. You get the AC wave tries to get too big and it gets chopped off, and you get what's called clipping distortion. So a low impedance microphone to a high impedance amplifier input is not good. But let's see what happens if we take a high impedance output to a low impedance input. Now this says, I need a lot of current. This says, sorry boss, I'm a high impedance. I can't give you much current. So what's going to happen? We're going to get a voltage sag here, and we're not going to develop much voltage across here. Let's take a look at an example of how that might be. Let's say this is 20 volts. And let's say this is, how about 9K, and this is 1K. So a high impedance going to a low impedance. What's going to happen here? Well, I'm going to lose about 18 volts going across here, having only about 2 volts left over. We can just look at this as a voltage divider. I have 9/10 of my resistance here, 1/10 of my resistance there, so I get 1/10 of my voltage, 9/10 of my voltage. So my 20 volts, I lose 9/10 of it, that's 18 volts. Leaving 1/10 of it, 2 volts left over. So if I go from a high impedance to a low impedance, that's going to be problematic. I'm not going to get much voltage left over here. There might be some rare cases where that's desirable, but usually it's a problem. For example, if I have a PA system and I take a high impedance microphone to a low impedance input, I'm not going to get the amplification I expect because the input voltage is going to be too low. So just like if I take a low impedance microphone to a high impedance input, I get too much voltage. The signal tries to go too high and too low, it gets clipped off, I get distortion. A low impedance microphone, or should I say a high impedance microphone to a low impedance input, I don't get enough of a signal to amplify. So that's usually a problem. So let's look at that again. Just a quick review. Low impedance to low impedance, that's good. Low impedance delivers a high current. This needs a high current. They work together. High impedance to high impedance is good. This doesn't need much current. This can't deliver much current, so they work together. A low impedance to a high impedance is usually good because I maintain my voltage. I don't have much voltage drop across it. But if I have a high output impedance to a low input impedance, I'm going to get a major voltage sag here, and I'm not going to get my voltage transferred over. So that's the problem. So low to low, high to high, low to high is almost always good, but high output impedance to low input impedance is usually problematic. Now let's say I have a situation where I want to get the maximum current across my load. This is desirable in a couple of places I can think of off the top of my head. For one, radio transmitters. You want to develop the most power you can across the antenna to transfer as much energy into the luminiferous ether and create the strongest radio waves you can. And when it comes to audio amplifiers, you want to deliver the most power to the speaker you can because you want that power turned into sound waves. And so in both cases, you want to develop the maximum power on the output. In those cases, you want the impedances to match. So I want, for example, let's say this is a 50 ohm impedance. I want this to be a 50 ohm impedance. So this is a common situation in radio because a lot of antennas, just by the nature of the way they are built, happen to have a 50 ohm impedance. So then we have to design the transmitter to also have a 50 ohm impedance to get the maximum power across that antenna. Let's see how this works. So we have 20 volts there, 50 ohms, 50 ohms. I'll use my trusty calculator to get these numbers. Let's see how much power we're going to develop across this resistor. So we have 50 ohms, that's 100 ohms. And we're going to divide that into our 20 volts. That's going to give us 200 milliamps. So what's the power? 200 milliamps, I squared times R, that's going to be that's going to give us 2 watts. So at 50 ohms, I get 2 watts of power. Let's see what happens if I drop this down to, let's say, let's make it 10 ohms. Let's see what happens to our power. So now we have 60 ohms, goes into 20 volts. That gives us a current of 330 milliamps. So what's our power going to be? That's going to be I squared R, so 330 times. That's going to give us 1.1 watt. So we reduce this to 10 ohms. So at 10 ohms, we only get 1.1 watt. So let's go back up to 50 ohms. Just momentarily. So at 50 ohms we had 2 watts, but we reduced this to 10 ohms, we went down to 1.1 watt. So if we increase the resistance, we should get more power, right? Let's see what happens. Let's put that up to, nice even number, how about 75 ohms? So now we're above 50 ohms. So now we have 50 and 75, that's going to be 120 ohms. 20 divided by 120 gives us a current of 166 milliamps. We square that, multiply it by the 75 ohms. So we do that and we come out with, at 75 ohms, have a higher power? No. We have 1.9 watts. So notice the power dropped again. So to get the maximum power across our load, we want the load impedance to match our output impedance. So for a quick review, Thevenin's theorem says that a circuit, no matter how complex, will act like a single voltage source with a single impedance in series with that. And we've proved that by a little bit of mathemagic on the board here. And the Thevenin equivalent impedance is the output impedance of the circuit. And so we have an output impedance and an input impedance, and those two interact with each other. High impedance is associated with low current. Low impedance is associated with high current. And so if we have a low impedance and a low impedance, that's good. We get a good match there. If we have a high impedance to a high impedance, that's a good match. A low impedance to a high impedance is usually a good match. Some exceptions that I talked about earlier, but when we have a low impedance here and a high impedance here, we preserve our voltage across there, which is usually desirable. But if we have a high output impedance and a low input impedance, we have a voltage drop and we have a significant loss in the voltage. So that's usually undesirable. So the one thing that's undesirable is to have a high output impedance and a low input impedance. They don't work well together. And finally, if we want to maximize the power, develop the most power across our load, we want the load impedance to match the output impedances, as I showed here. We get our maximum power across our input impedance if it matches the output impedance of the circuit driving it. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.